Hi, welcome back to CS560. So today we're gonna begin an important topic, which is about the growth of functions. So as a brief review of the previous contents, when we describe the running time for sorting algorithms, we talked about two sorting algorithms, the insertion sort and the merge sort. And we know that the running time for insertion sort, even if it's a average case, it's still a quadratic running time function. And the running time for merge sorts, it is the function that we use to describe the running time is big theta of n times logarithm of n. Okay, so in the previous video lectures, we have described how we obtained these solutions. Okay, so here in this lecture, we're going to go through a couple of formal definitions that specifies the rules, the mathematical expressions that will be used to describe the growing speed of different types of functions. Okay, so here we want to use an example to show a comparison between insertion sort and merge sort. And we basically want to show that's why merge sort runs faster than insertion sort. Okay, and as we know that the big theta notations, they are kind of simplified notations because they using big theta means that we ignore the constant terms in the expression. For example, an actual insertion sort algorithm can actually run on a very fast computer, right? So that means that the constants associated with the quadratic function could be very small. Yeah, so here we use the coefficients 1 to indicate that it's a pretty fast computer, which brings very little constants overhead. And for the merge sorts, and we assume that it's running on a very slow computer, which brings in a very large constant factor, which is 100 here. So the running time for merge sort is 100 times n times logarithm of n. So we want to use this extreme comparison to show the advantage of merge sorts. All right, so now let's look at different values of the input size and how the values will result in the performance of the two algorithms. So on the curves here, the blue, the green one is the function of the merge sort, which is n times logarithm of n, and the red curve is a quadratic function. Okay, so as we see in this first plot, when n is smaller than 500, the merge sorts, the running time of merge sort is always greater than the running time of insertion sort, which means merge sort is slower. Okay, so this is not an ideal case for merge sort because it is running on a very slow computer, which is basically why merge sort doesn't perform better than insertion sort. But don't worry, let's increase the input size a bit from 500 to 1000. So when we reach the point of 1000 here, the two curves merge, right? So if in the case of sorting 1000 and an input array of 1000 elements, merge sort is as fast as insertion sort, even if, do not forget the fact that we are running on a slow computer, which brings in a very big constant factor. All right, so let's further increase the input size, and I think you will guess the result, right? Because the momentum goes on, the quadratic function keeps growing faster and faster, and the merge sorts, the curve of merge sorts is much flatter compared with the insertion sorts. So when we consider larger input sizes, which is way beyond 1000, then insertion sorts is going to cost much more time, even if it's on a very fast computer. Okay, so basically we are using the behavior of functions to describe the running time or to describe the efficiency of algorithms, okay? Because it is not the actual running time on a very specific problem that determines whether an algorithm is good or bad, but it is the general trend or how fast the function grows with input size that really matters. Okay, so that's a basic review of the previous contents and basically lays out the purpose of this chapter. So we are gonna introduce a concept called asymptotic efficiency, okay, which basically summarizes what I talked about in the previous slide. So asymptotic efficiency is something we care about when we analyze the efficiency of algorithms, okay? It is the order of growth of the running time function that matters, not the actual amount, not the actual value, okay? So this is the so-called asymptotic efficiency of algorithms, okay? It basically describes how the running time increases with the input size n in the limits, okay? As n increases without bound. We need to consider the most extreme cases because we don't know how long or how big the input could be. So that's why we are considering this asymptotic efficiency. Okay. So usually when we choose between algorithms, we would always choose the one that has the asymptotically more efficient choices, the more symptotically efficient ones. So let's just go back to the previous example. Maybe the merge sort, it behaves better in a smaller range of inputs, but asymptotically speaking, it eventually will be the better choice. That's our basic principle of choosing algorithms. Okay. So we're gonna introduce a bunch of asymptotic notations, including the big theta notation, big O, and the big omega notations. We're gonna introduce their mathematical definitions one by one and how they are applied and how they are correlated with each other. Okay, so first of all, these notations, they apply to functions. Okay, for example, when we describe a quadratic function like a times n squared plus b times n plus c, then we can use the big theta of n squared to describe this function. We say that this quadratic function falls into the category of big theta of n squared. Okay, so these notations describes the asymptotic properties of functions. Okay, and usually they are used to describe the running time of algorithms because we use functions to describe the running time of algorithms. Okay, and sometimes we can also use them to describe the amount of memory space. Okay, but memory space is not the primary concern of this course. Basically, we care about more about the running time. Okay. So from the next video, we're gonna introduce the big theta and big O and big omega one by one.